Yesterday, at the beginning of our notes, we talked about if two events are independent versus when two events are dependent. So just reviewing those definitions again. Quickly, if my first event is flipping a coin and my second event is spinning a spinner, does flipping a coin have any effect on what the spinner is going to land on? And the answer is absolutely not. So these are two events that we would consider independent. And we consider them independent because the first event, flipping a coin, has no effect on the outcome of spinning a spinner. Versus, now take a look at my second selection of events. My first event is picking a card from a deck, standard deck of 52. I keep that card and don't put it back. And then I pick another card. These two would not be independent. They'd be what we call dependent. Why? Because when I kept that first card from the deck, now my options are one less when I pick the second card. Because remember, there's 52 cards in a deck. Now there's only 51 when I keep the first one. All right, now there's only 51 for my second choice. So if the first event has any effect on the outcome of the second one, we call it dependent. Dependent. And today's notes, the last day of the notes for the unit is, if I give you two scenarios, two events, you'll be able to tell me if they are independent of each other or they depend on each other. They're dependent. And it's going to be mathematically proven. You can't just use your opinion on it. All right, no opinions here today. I want it mathematically proven. Yes, these two are independent, or no, these two are, or yes, these two are dependent on each other. There are two ways you can test. There are two ways to test if an event is independent or dependent. We're going to go over both options today. First option, when you calculate the probability of one event given the other, so A given B, when you calculate that probability, how do you calculate it? Remember, it's on our formula sheet from yesterday, right? It's on our formula sheet. It's number 3 on the formula sheet we did yesterday. When you calculate that probability is the exact same probability as the probability of event A all by itself. All right, so we need to calculate the probabilities of both, look at them. If they're equal, the two events are independent. If those two are different, they're going to be dependent on each other. So that's exactly what we're going to do here in example 1. First thing we know, probability of Josh being late is 0.3. So him being late is 0.3. The probability of Josh being late given that he missed the bus is 0.9. Can we say these two, Josh is late to school and Josh missed the bus, are they independent or dependent? And again, I don't care about your opinion. No offense, but I don't care. I don't want to hear, oh, of course he's late because he missed the bus. Well, I could argue too, maybe he's late because his alarm clock didn't go off. All right, so no opinions here. We want to mathematically prove that yes, they're independent or yes, they are dependent. So yesterday in class, I suggested making up your own symbols, like Josh late to school. Some of you may have an L, some of you may have an S. I'm going to go against that now. All right. And the reason I'm going to go against that is because all our formulas have A and B's in them. So why not just call one A and one of them B? So in this case right here, Josh is late to school. I'm going to call A. Josh missed the bus. I'm going to represent as B. So anytime we talk about being late to school, that's going to be A. Missing the bus will be B. So are these two independent or not? Let's test this out. If they are independent, the probability of A given B should be the same as the probability of A all by itself. All right, so let's see if we can figure out what these probabilities are. Well, the probability of A, Josh is late to school. All right, Josh is late to school. Look back at the problem. That was given to us as 0.3. Okay, 0.3. What about the probability of A given B? The probability that Josh is late to school given he missed the bus. All right, what's the probability that Josh is late to school given he missed the bus? Look back at what was given to you. That probability was right there for us. Look, Josh being late And the probability of Josh being late, given he missed the bus, is 0.9. So that's going to be 0.9. Notice they are different from each other. They are different, which means these two events are dependent. Yes, it did matter that he missed the bus because he was late to school. So these are dependent. Now, I wish it's going to be that easy where the whole problem, they give you both values. We may have to calculate either one of them, okay, or both. But right now, these two are dependent because 0.9 is not the same as 0.3. Okay, so hopefully we're good there. Just soak that in for a second. Take a look at everything we just did right there. Okay, that's the first way. We can tell if two events are independent or dependent. That's the first way. The second way is using the other formula that's on the bottom of your formula sheet, and that is if two events are independent, if they're independent, the probability of A and B, I know we had a symbol for that yesterday, is going to be the same. That probability is the same as the probability of A times the probability of B by themselves. Okay? So either way, I can test if two events are independent or not, depending on what the problem gives me. All right, now let's read through here. Probability of Kim having pizza for lunch on Wednesday. So pizza for lunch, 0.4. Pizza for dinner, 0.3. Okay, so pizza for lunch, 0.4. Probability that she does both lunch and dinner. Okay, so lunch and dinner is 0.05. So what can you tell me about Kim having pizza for lunch and Kim having pizza for dinner? All right, are they independent or dependent on each other? So again, let's keep with our A's and B's. So pizza for lunch, let's call that A. Pizza for dinner, let's call that B. Okay, let's call that B. Now, why don't I want to it might not be a good idea to use the formula I just showed you, the test we just did for the first one. The reason being, I don't see the probability of lunch given dinner. I don't see any of that word given here. All right, so it's that formula is not going to be too easy to use. Versus this one, now I can say the probability of A and B, is it equal to the probability of A times B? All right, so let's see if we can fill them out because we are given both probabilities in this problem. What's the probability of lunch, pizza for lunch, and the probability for pizza for dinner? That was 0.05, right? So 0.05. Is that the same as the probability of pizza for lunch? Take a look back at your problem, guys. Take a look back. What was the probability of pizza for lunch? Looks like it was 0.4 times, what's the probability of pizza for dinner? Pizza for dinner, if you look, was 0.3. 0.3. All right, well, let's see. Do they equal each other? Is 0.05 the same as, now grab your calcs. Let me know what 0.3 times 0.4 is going to be. I have 0.12. So these are not equal to each other, so we say they are dependent of each other. All right, dependent. So there's two different tests we could do. And which test we pick really depends on the information we're given. All right, again, it's on your formula sheet. I'm going to let you have it on the test on Friday. Under number 4, we can say two events are independent if the probability of A given B is equal to the probability of A. Or we could use the probability of A, I'm going to start using my symbols from yesterday, and B is equal to the probability of A times B. We can use either one. I don't need you to use both, but use one you're going to be comfortable with given the information. All right, now, both of these last examples, every single value we needed was already there. What if it's not and we have to calculate it? All right, so here's our table again with the under 5, over 5, under 14 years old, and over 14 years old one. So what I want to know here is the person over 14 years old and the person is over 5 feet tall. Are they dependent or independent? Well, let's start by calling 1A and 1B. You will notice here we are going to have to calculate some probabilities on our own. They will not be given to us like they were in the last two examples. So let's go over option test number 1. If we go back and test number 1, the probability of A and B has to be equal to the probability of A for them to be independent. Find both probabilities and let's compare them. So the probability, let's first start with the probability of A, the right side. The person is over 14 years old is what we called A. So go back, this is going to day 1 now. What's the probability the person is over 14 years old? Well, there's 70 of them out of the total of 100. So there's the right side. Left side, how do I calculate the probability of A given B? So the probability, ready? What's the probability that the person is 14 years old given the person is over 5 feet tall? We did this on day 1. That's why I did it with you, to get to this point. So look at your table. The probability the person is 14 years old given the person is over 5 feet tall. So I'm only looking here because it's already given they're over 5 feet. So it's going to be out of those 67, how many are over 14 years old? 58 of them. Now, just by the looks, I have no idea if these two are equal to each other. No idea. All right, but that's why I have my calculator. So we go to the calculator, 58 out of 67 gives me about a 0.865. And then over here, 70 divided by 100, 0.7. All right, so you guys can see clearly they're not equal, right? So we would say dependent. Now let's say you don't feel comfortable doing the test number 1. There's a second way to test if they're independent or not. Ready? We can do the probability of A and B is equal to the probability of A by itself times the probability of B by itself. All right, so let's go back to our table to find these probabilities. The probability the person is 14 years old and over 5 feet tall. Where is that in the table? The person is over 14 and over 5 feet tall. Let's see, over 14, over 5 feet tall, looks like to be 58 of them, right? 58 out of 100 total. 58, both happen. Now, let's do them separately now. Probability the person is over 14 years old. What's the probability in this table? They're over 14 years old. Looks like 70 out of 100 times the person is over 5 feet tall. How many people are over 5 feet tall in the entire table? 67 of them out of 100. Again, I have no idea if these two are equal until I type them in my calculator. I know that's 0.58. Now I go to my calculator, 70 over 100 times 67 over 100. And I get 0.469. So again, even using the second test, they're also dependent. On the test Friday, all right, on the test Friday, I don't care what method you do. All right, however you want to do it, whatever you're comfortable with, and really whatever you have enough information for too. All right, either method was nice here because we had a darn table to work with. Same thing, next example, go ahead, if we're working with a Venn diagram. Okay, both options are real nice on a Venn diagram. So let's go through here. Person likes frozen yogurt and the person likes mustard. Are they independent or dependent? So we'll call this one A. We'll call this one B. Okay, we'll call this one A and B. So option one, are they independent? Well, if they are, they'll fit into this. All right. So let's see here. Let's do the right side first. So given the Venn diagram, what is the probability that the person likes frozen yogurt? What is the probability they like frozen yogurt? Well, 87 of them only like frozen yogurt. 33 of them like both. So we do have to count those in there. So it looks like we have, let's see, 120 of them out of, I think it's 200, right? Or 7. So we got 87 and 33. Let's just add those up real quick. 58 plus 22 plus 33 plus 87. Added 200. Yep, that's what I thought. So added 200. Is that the same as a person liking frozen yogurt given they already like mustard? All right, so given they already like mustard. So it's not going to be out of 200 anymore. It's going to be out of the people that already like mustard, which is 33 and 22, 55 of them. So out of those 55, how many like frozen yogurt? Looks like 33. Again, can't tell. So we go to, can't tell if they're equal. So I go to the decimal version on my calculator. I get 0.6. And then over here, 120 divided by 200. Ho-ho! We got a winner. Finally, huh? Yes, they are independent. It does not matter if you like mustard or frozen yogurt. One does not have any effect on the other. All right, I still want to do option 2 though. All right, test number 2, which is probability of A and B is the same as the probability of A times the probability of B. All right, A and B. So how many people like frozen yogurt and mustard? That's the intersection, 33 out of 200. Is that the same as these all by itself? So how many people like frozen yogurt? Well, we said what before? That was 33 and 87, which gives me 120 out of 200, times the people that like mustard. So that's 22 and 33, 55 out of 200. So now we go to the calculator. 33 divided by 200 gives me 0.165. And then let me do the multiplication on the other side. 120 out of 200 times 55 out of 200. Oh, let's go. 101.165. Check. So we can confidently say, doing either test, that liking yogurt and mustard independent of each other. Independent of each other. All right. Should hopefully no questions there. I think we're okay. Just looking at some of the stuff I'm having you do tonight. Everything's good. All right. So you guys can get working. I'm not going to do this one, this harder example, multi-step. I'm not going to worry about it. Nothing like that's going to be on the test. I want you guys to start working now. All right. So start working. Take your answer key out on Classroom and start working on the assignment. And we'll talk on Thursday, tomorrow, if we're going to do the test on Friday or Monday. Thanks, guys.